Hi everyone, this is Mrs. J, and today we're going to learn about special functions. I have a quick warm-up for you guys, so please pause the video and give it a try. Alright, go ahead and check your work here. So this is a little review of graphing a linear equation and then practicing describing all of those key features that we've talked about in previous lessons. So note, I did use interval notation for this one. If you use a different notation, that is completely fine. So the first special type of function we're going to talk about is what's called a piecewise function. So it's kind of what it sounds like. It's a function made up of different pieces. So it is when you have a function that is defined by two or more expressions, where each expression is defined by a different interval over your domain, which is your x value. So here, we're going to start by graphing this piecewise function. So you see this is how they look. You'll see f of x equals, and you'll have a large brace that's encompassing all of the pieces of your function. So you can see that this function is split up into two pieces. It's represented by the expression x minus 4 for all x values less than or equal to 1. And then it's represented by 2x for all x values greater than 1. So whenever we are graphing a piecewise function, whether it is defined or not for that piece, we are always going to substitute that crossover point into both parts. So I am going to substitute 1 into both pieces of our function. And if it's a part that's inclusive, I'll use a closed coordinate, so a colored in coordinate. And if it's from the piece that's non-inclusive, I'll use an open coordinate. But we need to know where those endpoints are for that transition point. All right, let's start with this first portion of our graph, this x minus 4. So I am going to start by substituting 1 into that portion, and we get negative 3. So we know that we have the coordinate 1, negative 3, and I am going to use a closed coordinate because it is included. Now, I could do a few different approaches for this. Since it is everything to the left of 1, it will cross my y-axis, and I can see from the equation that the y-intercept is at negative 4, so that's a useful point for us. And if you have 2 points in a linear equation, that's enough to connect them and graph. But we could have also used the slope of that portion, which we can see is 1, always the coefficient of x, so we could have just followed that slope moving backwards to the left. So you can see this portion does have a slope of positive 1. Now let's look at the next portion of our graph, the next piece, which is defined by 2x. So I understand that 1 is not defined for this piece of my graph, but I need to know where that endpoint would be. So I still need to substitute 1 into that portion. So it's going to be at 1, positive 2, and for that I'm going to use an open coordinate, again because it just says greater than, and then it is going to continue on to the right. So for this one, we're just going to follow our slope, which we know is positive 2, to the right to help us find more points. So it looks like this. So it's really, really common for piecewise functions to be discontinuous. Notice I need to physically pick up my pencil to graph this function, and that's completely fine. Sometimes it will actually make a continuous function. One piece will pick up where the other one left off, but usually you will end up with a discontinuous graph. So again, the important thing is to always make sure you have that endpoint defined. So whatever this number is, you are plugging it into both, and just be careful if you use an open or closed coordinate. All right, so here I have one for you to try on your own. So pause the video and give it a try. All right, go ahead and check. You should here have an open coordinate at negative 4, negative 1. Let me write that coordinate down, negative 4, negative 1. That's that kind of endpoint for this piece of our graph. And again, it should be an open coordinate. And then you should have a closed coordinate at negative 4, negative 5, which you can see right here. And then you would follow the slope of 3 over 2 going to the right. And then for this portion, you kind of work backwards. You make sure it has a slope of negative 1 over 2. So I went up 1, left 2. And if you continued on that pattern, you would see that you would hit your y-intercept at negative 3. All right, the next special function we're going to be working with today are absolute value functions. So anytime we introduce a new family of functions, I'm typically going to have us make a table to plot what's called the parent function. So the parent function is kind of the most basic form of that type of function. So in this case, it's just y equals absolute value of x. So remember, absolute value signs take whatever's inside and they make it positive. So whenever you see those vertical lines, it's absolute value. So let's complete this table of values. If I insert -3 right here, the output will be +3. Then we have 2, 1, 0, and 1, 2, 3. Remember, if the inside of an absolute value is already positive, it just stays exactly the same. So if you plot those points, you get a graph that looks like this. So absolute value functions will always make these V-shaped graphs. They actually do come to a point. They're not curved ever. And really, it's just two linear functions put together. So we actually will be practicing writing all absolute value graphs as a piecewise function. It's just two linear functions. But always expect to have that V-shaped graph. We will always have a vertex. That's the pointy part of our graph. So it's important to know these key features and how to find them based on the equation. So this is kind of a more, the more common way you'll see these functions. So we have y equals a times the absolute value of x minus h plus k. So it's very possible that you have something being multiplied in front of your absolute value. It's possible that you have something added or subtracted from x, and then it's also possible that you have something added or subtracted outside of your absolute value. So these features, or these three variables besides x, will help us determine some key points. Probably the place I always like to start is with the vertex. That's always that pointy part. So your vertex is always going to be at hk. So notice h is whatever is being added or subtracted to x, and k is whatever is being added or subtracted on the outside. Another thing I want to point out is in this form, it says x minus h. Because we have this minus here, it's implying that it's the opposite. So notice this says minus h and this just says h. So we're really going to have opposite signs here, but for the k value, it's always going to be the same side. So be careful with that h value. Our domain is always going to be all real numbers for these types of functions. And our range is always going to be everything from our vertex up, or if we have a negative out front, it's actually going to flip our graph, and then it's going to be everything from our vertex down. So for this form, assuming a is positive, our range is actually going to be k to infinity. So this k value, again, is the y value of your vertex. So it's either going to be the high or low point of our function. Now, the slope to the right of our vertex is always going to be whatever that a value is. And if they have a negative out front, it will also be negative. And then the slope of to the left of our vertex is always going to be the opposite of that a value. So notice here, for our parent function, to the right of our vertex, the slope is +1. And then you could see to the left of our vertex, the slope is -1. So that will always be true. The slope to the right and left of our vertex will always be opposites, and is always going to be dictated by that a value out front. So now that we know the basics of an absolute value function, I want us to practice writing it as a piecewise function, which is going to be a really important skill kind of as you progress through higher levels of math. We actually do this all the time in calculus, so it's important that you know how to write any absolute value function as a piecewise function. So let's just do this parent function here. So we can actually see the crossover point. The crossover point is always going to be the x value of your vertex, which in this case is at 0. So let's set up our function. We have our large brace. So let's start with to the right of our vertex. This is just a linear function that has a slope of 1 and a y-intercept at 0. So this function is just defined as x. Now we need to define the interval of x, so that's going to be for all x values greater than 0. And we can include 0 in this in this portion or in this portion, it doesn't matter. I'll include it in our top piece. The only thing is you cannot include it in both because then it's no longer a function. And then to the left of our vertex, you can see that it's a linear function with a slope of -1 and a y-intercept also at 0. So it's just going to be -x, and that's going to be for all x values less than 0. So you can see, again, it doesn't matter where you put that or equal to sign. It can go in the top or the bottom, just not both and not neither. So we are going to practice writing more complex equations or absolute value equations as piecewise functions, but we'll also practice graphing them just based off what we know where the vertex to be and using a as the slope to the right and the opposite of a as the slope to the left. All right, let's give this first one a try together. So first and foremost, with absolute value functions, I'm always going to simplify it whenever I can. So if I have the absolute value of 3/4x, I know that the absolute value of 3/4 is just 3/4. So we can actually just pull that portion out front. Now, I can't pull the x out front because x is the independent variable. It can be anything. It could be a positive, it can be a negative. It needs to stay inside our absolute values. But any constant, we can pull it right out front, and it makes it a little bit easier to graph. So now looking at this, I see that there's nothing being added to our x value. So if I'm trying to define the vertex, which is going to be the first thing I want to plot, I can see that the x value of the vertex is going to be 0. That h value is 0, and my k value is just 3. So I know that my vertex is going to be at 0, 3. So right here. And then I know that that a value, which is 3/4, is going to be the slope of my function to the right. So slope to the right is going to be 3/4. And that means that the slope to the left of the vertex is going to be the opposite, -3/4. So if I go back to my vertex, moving to the right, I go up 3, right 4. I'll do that one more time. And then I know the slope to the left is the opposite. So I'll go up 3, left 4, up 3, left 4. And you should have a symmetrical graph as well. If you drew a vertical line through your vertex, it should always have that line symmetry. So you should get that nice V-shaped graph. So now we have our graph. Now we're going to practice writing it as a piecewise function. So whenever you are writing something more complex as a piecewise function, first thing to note is that that turning point is always going to be at the x value of your vertex. So you can see to the right and left of 0, we have two different linear equations. So anything to the right of your vertex, you're essentially just going to turn your absolute value signs into just parentheses. It's essentially saying the part of your function that was already positive, so the absolute value signs really aren't doing anything. So for that portion of our graph, again, anything to the right of our vertex, your absolute value signs are essentially not doing anything, okay? So this is going to be for x is greater than 0, or you can include 0 here, doesn't matter. But then we need to figure out the equation to the left. So we already know, we can look at our graph and we can make the equation. We know that the slope is -3/4, and we know that it has a y-intercept at 0, 3. But we're not always able to see that y-intercept so nicely. So anything to the left of our vertex, essentially anything inside our absolute value should be made opposite. And then we're just going to simplify that. So it does just become -3/4x plus 3. And that's going to be for everything, for all x values less than or equal to 0. And again, it doesn't matter which piece you include 0. Could be here or here, just not both and not neither. So there you have it for this example. All right, let's try another one together. So this one, we can't really simplify anything inside, you can't just pull out a +1. You can only do that if you have a factor or something being multiplied. So this is as simplified as it can be, but we can start by determining our vertex. So remember, for your vertex, whatever is being added or subtracted from x is going to be the x value of vertex, but it will always be opposite. So since I see +1 here, my vertex is going to be at -1. And then here we don't see anything added or subtracted on the outside, so that y value will just be 0. So in this case, my vertex is at -1, 0. So it's right there. And then I look at that a value out front. And here we actually have a negative as well. So that tells us that the slope to the right of our vertex is going to be -2. And that means that the slope to the left of my vertex is going to be the opposite of that, which is +2, or you could just think of it as reflecting it over that line. So I go back to my vertex, and going to the right of it, again, I'm going to follow a slope of -2. So I go down 2/1. And then to the left of my vertex, my graph is going to have a slope of +2. So it looks like this. And again, you can see that we will need to write this as a piecewise function. So everything to the right of our vertex, let me write to the right. And this time, our vertex is at -1, 0. So this is going to be everything to the right of x equals -1. We essentially just turn our absolute values into parentheses. It's essentially saying we're looking at the values that were already positive, so the absolute values aren't doing anything. So it just becomes this, and then we'll just simplify that. So -2x minus 2. So that's going to be everything to the right of x minus 1, but everything to the left of our vertex, so to the left of x equals -1, we're essentially looking at the values that were negative, but the absolute values made them positive. So we have to make everything inside opposite. So I'll set up an equation like this. So we have -2. My absolute values turn into parentheses, but everything inside becomes opposite. So it actually becomes -x minus 1. So again, we're looking at all of the values that were negative that the absolute values made positive. Everything inside becomes negative, and then we just simplify. So we get 2x plus 2. And we can kind of check to see if these make sense. To the right, we do see that we have a y-intercept of -2, and the slope is -2. Here, our slope is +2. If you continued this on one more point, it would hit that y-intercept at 2. So we know that these two equations are correct. So now we just need to write them with the correct notation. So we'll say f of x equals, and then we have -2x minus 2 for x is greater than or equal to -1, so to the right of -1. And then we have 2x plus 2 for when x is less than -1. So that is the piecewise version of our absolute value function. And this is always how you can find it. Everything, again, to the right of our vertex, the absolute values are doing nothing. They literally just change to parentheses. Everything to the left of our vertex, everything inside the absolute value becomes opposite. All right, we're going to try one more together. So here you see that we have this 3 that's being multiplied to x. So remember, we want to try to pull those out of the absolute value whenever we can. However, this is a binomial. I can't just factor a 3 out of this part. I need to factor it out of that entire binomial. So my first step is going to be factoring it within the absolute value, like this. And now I can take this factor of 3 and pull it out front, because the absolute value of +3 is just +3. And then I am left with just the absolute value of x minus 2 minus 5. So this is going to be a little bit easier for us to work with. And we want to do this so we can determine what our vertex is. From this form, we can't look at it and say my vertex is at positive 6, 5. The coefficient of x does need to be 1. So we do need to make sure we're factoring out this value and pulling it out front. So here I can see that my vertex is going to be positive 2, negative 5. Remember, whatever's next to the x is always opposite, but whatever is outside, it stays the same. And then I see that the slope to the right of my vertex is positive 3 over 2, and the slope to the left is going to be negative 3 over 2. So that will give us enough to graph. So let's start with our vertex. So we have 2, negative 5, so right here, and our slope to the right is going to be 3 over 2. And then our slope to the left is negative 3 over 2. So we're going to move in the opposite way. There we go. We have our nice V-shaped symmetrical graph. And now we want to write this as a piecewise function. So I'm going to just use this form to help us do that. So remember, everything to the right of our vertex, and we're going to use the x value of the vertex. So everything to the right of x equals 2, essentially the absolute values are doing nothing. So we have 3 over 2 times x minus 2 minus 5, and we will want to simplify that. So we have 3 over 2x, and then if I distribute here, we get minus 3 minus 5, so we get minus 8. And then everything to the left of our vertex, so at x equals 2, remember everything inside our absolute values needs to become opposite. So we have the 3 over 2 times negative x plus 2. So the x becomes negative x, negative 2 becomes positive 2. Everything becomes opposite. And then here I'm just going to simplify again. So we have negative 3 over 2x. And then here we'll have plus 3 minus 5, so minus 2. And then we're just going to write this with the correct notation. So big brace. And then we have 3 over 2x minus 8, and that's to the right, so when x is greater than or equal to 2, and then we have negative 3 over 2x minus 2 for whenever x is less than 2, which just means to the left of our vertex. And we can always go back in and kind of double check to make sure that this looks right. If you continued on this graph, you'd see it would hit that y-intercept of negative 8. And you can see that this graph does actually have a y-intercept at negative 2. So there you go. So just remember, simplify your function first, and then you can use this form to find the vertex and our slopes. And then you could also use this form to define the right and the left half of your graph. Okay, I have this last example for you to try on your own, so please pause the video. All right, go ahead and check your work here. From this form, we could see that our vertex is negative 2, negative 6, and we know the slope to the right is 1/2, and the slope on the left is negative 1/2. Then here's my equation to the right. Again, absolute values just turn to parentheses. And to the left of our vertex, everything inside the absolute value becomes opposite. And then I just distribute and combine like terms. And again, my crossover point is always going to be the x value of the vertex. All right, that is all for today's video. Thank you so much for watching.